previous lecture, I showed the rising of bands through a simplified version of Kronig-Penney model. That consisted of periodic potential made up of delta functions. So, V x was given as summation m minus infinity to infinity V delta x minus m a. And what I showed is that if you go through the boundary conditions and Bloch's theorem, you get an equation cosine k a equals cosine of alpha a plus m v over 2 h cross square alpha sine alpha a, where alpha is square root of 2 m e over h cross square, and this leads to a picture for the satisfaction of the equation like this, and energies exist because the right hand side should remain below. Energy bands exist because the right hand side should be between -1 and 1, and therefore, energies exist only in these bands. And when we plot it, which you will do as a practice, the way you get these bands are, if you restrict between minus pi by a and pi by a, you get energy bands like this. And so on. Notice that the minimum exists or maximum exists only at k equals 0, and minimum or maximum exists at pi by a. And I left that question for you to think about in the previous lecture. Let me answer that now. So, if you look at this curve that we have been drawing, the right hand side of the equation looks like this, and +1 and -1 are right here. And energy is in this band. Notice that where the minimum of the energy, first minimum exists right here, shown by thick red line, and I will call it E1, there cosine of k a is equal to 1, and that means k equals 0. If I restrict myself with k being between minus pi by a and pi by a, then the only answer for this is k equals 0. So, the first minimum exists at 0, which is shown right here. Then the maximum of the energy exists at this E2, shown by green vertical line, E2, and at E2 cosine of k a is equal to -1. So, this implies k is equal to plus or minus pi by a, and that is where you see this maximum right here shown by green. Next minimum exists at this bright green line shown here, again by thick bright green line E3, and that is where cosine k a is again -1, and therefore, k is equal to plus or minus pi by a, and so on. So, you can see how minimum and maximum of the energy bands exist at k equals 0 or k equals pi by a or minus pi by a. So, in this lecture, let us focus on what does it mean in terms of physical properties of a system when there are energy bands. So, for that, first let us calculate the number of states in a band, and this would also give us the number of electrons in a band. To do this, we need to count k. So, to do this, we need to count the number of k points in a band. Just like, recall, in metals we counted number of states by counting the number of k points. And what trick did we use there? We use periodic boundary conditions. So, use periodic boundary conditions. So, suppose we have this set of atoms which are forming a one dimensional metal, and this is extending from minus infinity to infinity. What we will do is, we will demand that over n atoms the wave function repeat itself. So, psi x plus n a be equal to psi x. Okay, this is the periodic boundary condition. This is equivalent to, recall, we had in metals psi x plus L equals psi x. This is equivalent to that. The L is replaced by N A, number 1. So, that is point number 1. Point number 2, the wave function is also normalized over N A, so that one state in N A carries exactly 1 electron for each spin. Now, to normalize it over N A, I can decide to normalize u, the wave function psi x, recall, is e raised to I k x u k x. I can decide to normalize u over the entire N A or over a cell, and that will just change my normalization coefficient, but that is immaterial right now. So, what the 2 point I am making is that 1 periodic boundary condition over N A, and 2 wave function normalized over N A. So, if we do the first point, I have e raised to I k x e raised to I k N A times u k x plus N A is equal to e raised to I k x u k x. Now, I can cancel u part because u is periodic. I can cancel e raised to I k x part, and what I get from the periodic boundary condition is that e raised to I k N A equals 1, and therefore, k equals 2 pi over N A times any number n. N varies from 0, 1, 2 up to n minus 1. Why n minus 1? Because for n equals n, k becomes 2 pi over a, which is equivalent to k equals 0. So, that state does not count. So, what this tells you that there are n k points in each band, right. Let me repeat it. Now, the band extends from minus pi by a to pi by a. So, that is an interval of 2 pi over a, and over 2 pi over a, k repeats itself. So, between k equals minus pi by a and k equals pi by a, there are n independent k points. So, with periodic boundary condition over n atoms, there are exactly n k points. All right. So, my system consists of this periodic thing over n, and then it repeats itself. So, I need to focus only on one part here. So, if I now plot the band, there are these n points. And each of these can carry 2 electrons. So, this means a band can accommodate maximum 2n electrons. So, suppose I have a band here. The maximum number of electrons can accommodate is 2n, and if each atom gives 2n electrons, this whole band would be filled. If an atom gives 2 electrons, the band will be filled. On the other hand, if an atom gives only 1 electron, band will be half filled. Now, if I take a half filled band, if the band is half filled and I give some energy to these electrons by a electric field, they may take energy and go to the higher levels, and that will lead to conduction. So, a metal is one where band is half filled. On the other hand, if I have a band which is fully filled, if I give energy to these electrons, they have no other place to go to. By Pauli exclusion principle, lower energy electron cannot go to the upper energy electron. So, they would not conduct. So, a filled band does not conduct, and this gives insulators. Now, if I have a band which is fully filled and next band which is close to it, the band gap is not much, this gap is very small, then some electrons can move to the upper band at temperature T, and then the lower band would be less than fully filled, upper band would have some electrons and they can conduct when electricity is given, and this gives rise to semiconductors. So, semiconductors and insulators are both systems where bands are filled at 0 temperature, but in insulators the band gap is very large and in semiconductors band gap is small. I am giving these arguments for one dimensional systems. Now, the 3 dimensional has little more subtleties, but idea is pretty much the same. So, bands explain how metals, insulators and semiconductors arise by filling bands and seeing if electrons there can absorb energy from an applied field. So, this is the implication of bands that arise in a periodic system. One question that often arises, whose answer I am going to give now, is when periodic boundary conditions are used over length L, why the wave function is also normalized over same distance L. We did this for metals, we did this for semiconductors just now, and this question is important because filling of bands, how many electrons can take, depends on precisely over what length am I normalizing the wave function. And the answer is that by applying periodic boundary conditions, one is implying that the system repeats, or better word is replicates itself over that length L, where the periodic boundary conditions are applied. So, a system really is extended over that length L over which I am applying the boundary condition. So, the system is given by that length L, and therefore, I normalize all my wave functions and everything over there, and that is what gives me the correct number of states, n number of k points over for n atoms and 2n electrons for the same number of atoms. So, to conclude, this lecture, we have explained the metals, insulators and semiconductors by bands formed in a periodic potential, and what we have said is half filled bands give metals, fully filled bands give insulators and semiconductors. This is for large gap and this is for small band gap. So, with this we conclude a brief introduction to formation of bands and how they explain semiconductors, metals and insulators. So, this concludes our course on quantum mechanics. I will give one more lecture to review the entire course.